typical embedded systems. This is a second chapter of Introduction to Embedded System by CBKV book. The main major outlines of this chapter are core of an embedded system, memory, sensors and actuators, communication interfaces, embedded firmware and other system components. So, as you all know, the embedded system means embedded, the dictionary meaning is hidden system. So, what is hidden in it? So, the when you examine embedded systems, you will find the system is built around a core, embedded core. The core might be any FPGA, ASIC, DSP, SoC and microprocessor and microcontroller. In most of the embedded system, the core is always a microprocessor or a microcontroller. So, this chapter 2 covers all the components of this embedded system. So, embedded means hidden. What is hidden? Core, memory, input output, sensors, actuators and intercommunication interfaces components, all are connected to core and kept in a box. That box we call it as an embedded system. So, in this chapter we have major outlines: core of embedded system, memory, sensors and actuators, communication interface, embedded firmware, other system components. I have recorded my lecture in 5 parts. The first part contains the core of embedded system, second part memory, third part of a video contains sensors and actuators, a fourth video as a part 4 communication interface, and I have recorded fifth part of this chapter 2, embedded firmware and other system components, in one last video. So, next in this video I am going to cover the core of embedded system. As you know, all the embedded system built around the core. Core is used in 80% of the embedded system. It is microprocessor or a microcontroller. So, we learn general purpose processors, application specific instruction set processor, microprocessors, microcontroller, digital signal processing processors, RISC, CISC processor architecture, Harvard von Neumann processor architecture, big endian and little endian processors, load operation and instruction pipeline. And even we learn about the PLDs, programmable logic devices, like CPLD and FPGA. So, the next just will have us this look at the slide. So, where the embedded system, this embedded system surrounded by us is shown in this slide. So, we are surrounded, according to the survey, surrounded around 100 to 200 embedded systems in India. The example for embedded system within our home are as we use a laptop, MP3 players, wireless phone, microwave oven, dishwasher, electric oven, smart fridge, washing machines, TV, MP3 player, mobile, remote, smart ACs, music players, electronic watch, etc. And even when you go outside, so we are surrounded by traffic light signal and a smart floodlight control, fire station alarm system. When you go to hospital, you have different gadgets like ECG and now the glycometer. And even when we go to the market in shopping malls, there also we are surrounded by different barcode readers and POS, point of service devices, and even in plane the cockpit has a different, and even for a service also has a different embedded systems are incorporated. So we are like this, we are surrounded by n number of different embedded systems. So once again we have a look at the elements of embedded systems. The embedded systems are built around the core. The core is always the microcontroller, can be a microcontroller or a microprocessor or a FPGA, DSP or SoC system on chip. Then the embedded system has a hardware, memory. Memory is required to store the program as well as data, and the embedded firmware to make the device work according to assigned function. The communication interfaces. The communication interfaces, we use some protocols to communicate external devices or external world. So input devices are usually keyboard, joystick, mouse, switches, push buttons, and all these are common interfaces. As an actuator or output ports, we have a LED 7 segment display units and LCD, piezoelectric buzzer or any such devices, etc. And other supporting integrated circuits or subsystems are codes, or it may be a brownout circuit, watchdog timer, oscillators, all such devices. So embedded system is the integration of all these, right, and programmed to deal with a specific task. So in this video we'll cover the core of an embedded system. This is the core of this embedded system. So major the core of the embedded system fall into any of these following. The core may be a processor, for example Core i7 microcontroller, 8051 ARM Cortex M3, and DSP processor, Texas Instrument DSP processors, PLDs, programmable logic devices, FPGA or CPLD, and application specific integrated circuits, ICs. So they are also called as a special purpose processors. So for example, so as you know already we have studied Verilog, and Verilog HDL is used to design the ICs. The ICs which are we design, for example adder circuits, that adder circuit is used for only single applications. That's why it's called as a single purpose processors, and these are called as a specific designs, only do that addition operation, not subtraction multiplications. So such devices are called such ICs are called as an application specific integrated circuits. And commercial off the shelf components, for example USB port we have. So even wireless mouse has one dongle. The dongle, when you insert in the USB port slot socket, then immediately it starts working. It doesn't need any drivers to load and all. Such such devices which are were helpful for plug and play are called as a commercial off the shelf components. Next, as you know, most of the embedded systems are the core is built around microprocessor and microcontroller. We should know a little bit more about the microprocessor and microcontroller. Just in this slide, we'll have a look at merits, drawbacks, application areas of a microcontroller and microprocessor. So microcontroller are a specific task. As already we have discussed about the definition, the microcontroller is a specific purpose, register based, clock driven, programmable, electronic device which stores the program in a ROM, accept the data in terms of binary, and processes the data according to the instructions stored in a ROM, and generate the result and store it in RAM. RAM is usually data memory. And the same definition it little bit we modify. The microprocessor is a unspecific task, or we can call it a general purpose. Right. So specific, I can give example mouse. Mouse is do a specific task. Only it is used to move the cursor from one place to another place on screen. Right. Microprocessor will do general work. For example, the microprocessor, a Core i7 used in a laptop, will do multiple tasks. For example, we can do in laptop, watch the videos, we can play the music, we can create the documents, and even sometime we can do multiple tasks at a time. But that not case in the case of microcontroller, which is specific only one work. Example I have given already, mouse. Mouse cannot be used, right, to do as a work such like in a remote operations and all. The microcontroller depends on input and need a definite output. For example, in case mouse, the definite output I know. What is the input? I am pushing the mouse, so at the same time that is the input what I am giving. The sensor senses the movement and the cursor will move on the screen. The definite output is movement of the cursor. But in a microprocessor, the output is not definite, because the microprocessor we use for multiple functions. That's why the output is not definite. Okay. The microcontroller are small resources. So small resources, RAM, ROM and all different ports are on single chip. And but in case microprocessor, we have to connect it externally. High amount of resource like RAM, ROM we have to connect. And the RAM, ROM, the size what we connect is large compared to the microcontroller. For example, 8051 is a microcontroller. On chip it has 4 kilobytes of ROM and 128 byte of RAM and 4 ports. The microprocessor 8086 we can connect 1 MB of RAM and ROM externally. A clock what is used is quite high in case microprocessor. For example, 8086 needs a 3 megahertz or more. Nowadays it is in terms of gigahertz. The processors what we have using the mobiles, they use they run on gigahertz speed clock, and the microcontroller few megahertz. For example, 8051, the microcontroller uses only 11.059 to megahertz clock externally and signals. And an ARM Cortex M3 microcontroller in lab we are using only 10 megahertz, okay, even though it can handle 100 megahertz. The microprocessor cannot be used as standalone, and the application areas of the microcontroller are in DVD player, washing machine, mouse, cameras, micro oven, as I already told. But application area of microprocessors are used in calculators, accounting systems, and game machines, industrial controls, data acquisitions, and military applications. So, general purpose processors, we will just have a look at general purpose processors and applications specific instruction set processors. General purpose processors are designed to do the general computation, and general purpose processor has a produced in the large volume, and compared to the ASIC application specific, the cost per chip is very low as it is produced in a large, and the general purpose processors has ALU and control units. The best example what I can give is the 8086 processor, already what you have studied. The application specific instruction set processors are processors with a architecture that is optimized for a specific domain. For example, for automobile domain, what is required, that amount of applications as instructions are incorporated and fabricated. For telecom domain, how many instructions are required, and how much, then even if you reduce the number of instructions, it will reduce the circuitry. So that is why based on the domain, the instruction set is optimized. Then the general purpose, for example, for application specific processors are automobile AVR, USB AVR for ATMEL systems. ASIC application specific IC. This is the IC what is unique application, it will do unique application, it is used as the replacement for conventional general purpose logic chips, and the total it consumes, it needs a very small area, and at the same time it is designed for smaller systems with the high capability and functionality, and the total engineering cost, non-recurring engineering cost for the fabrication of ASIC will be more, and a non-recurring engineering cost is born in third party, and the application specific ICs is made openly available in the market. So, to deal with the confusion between the general purpose processor, application specific processor, and ASIC, application specific integrated circuits, I have prepared this slide to make out the difference, so you should not get confused with it. The general purpose processors are designed for general computational tasks. For example, what do you mean by general computational task? For it may be a data acquisition, it may be some gaming, for video, watching video, playing videos, preparing movie, for example, and even document creation. So the i3, i5, i7, etc. are used in laptop and desktops or general purpose processors. They do multiple tasks. Application specific instruction set processors. These are the processors optimized for specific domain. For example, automobile domain, telecom, media applications, and digital signal processing. So, for example, automobile AVR and USB AVR chip, application specific instruction set processors provided by Atmel, and a DSP processor from a Texas Instrument, and the ASIC, application specific integrated circuits. These are the special purpose processors are optimized, or we can say fabricated for specific applications. As I told, already we have learnt a Verilog, and in a Verilog whatever the circuits we have designed while studying the subject. So, for example, adder. So, adder, once using the HDL we design and fabricate IC, that fabricated IC is used for only addition. It cannot be used for multiplication or any other functions. So, single function. So, these are the differences. General purpose, you can do multiple functions. Application specific instruction set processors optimized for specific domain. ASIC specially fabricated to do single function or a specific function. So, with this we will make out the differences between the microprocessor and microcontroller. So, here the microprocessor is represent the CPU of the chip, silicon chip, and where the highly integrated chip. Microcontroller is a highly integrated chip. So, here CPU, scratchpad RAM, ROM, ports are all on chip, on a single chip, timer, register, everything. It is dependent unit. It required external circuitry. For example, timer, memory, everything we have to connect externally. Self-contained units, that it does not require external interrupt controller, timer, everything is within a chip incorporated. Most of the time general purpose microprocessor is general purpose, microcontroller domain specific, does not contain a built-in IO port. So, if you want to extend the port, so we have to use some external chip help. For example, 8255, that is peripheral programmable interchip chip in 8086. To enhance the port capability, we use this 8255 external, we connected. But in case microcontroller, or in case ARM Cortex M3, so we have multiple number of ports built in. So, high end market, embedded is the market. Embedded systems use most of the time the microcontroller. So, in microprocessor we have limited power saving options. As you know already, the microprocessors are used in laptop and desktops. That does not require any power saving, as we always connected with. But in case mouse, wireless mouse, we have to use right battery, a cell, and then that is not connected with the charger. So we have, when I am not using, when I kept it ideal, it has to go, it has to shut down its operation, right. So this is the power saving feature all incorporated, as we use the in microcontroller is used in mouse. So this is the slide which will give the clear distinction between the microprocessor and microcontroller. So here everything is externally connected, RAM, ROM, IO port, timer and serial, and in a microcontroller all these are on single chip. So DSP processor. So DSP is a powerful special microprocessor designed specifically for computational demands and a power constraint in case embedded applications which are based on audio, video and communication applications. For example, MP3 player, music systems, communication applications, walkie-talkie or like such components. So DSP processor 2 to 3 times faster than the general purpose processors, and the key units of the DSP processors are memory, data, program memory and data memories. As you know already, program memories are used to store the programs required for DSP to process the data, and the data memory is used to temporarily store the variable or information or a signal information. Computational NG, for example MAC, multiply and accumulate, as we do in the signal processing more computations, that is why the MAC will be helpful. The IO unit, an interfacing between the outside world and a DSP. Application areas, the audio video signal processing, telecommunication, multimedia applications. And this is the block diagram which will give clear idea about the DSP processor. The analog signal is given as an input, ADC will convert, digital signal processing processor will process it, convert it into digital to analog is used to convert it into analog signal and then given as an input. So next type of the architectures of the processors or controllers are RISC and CISC. RISC architecture and CISC architecture. So first we will see the block diagram. RISC, CISC, RISC and CISC. RISC, reduced instruction set computer, and CISC, complex instruction set computer. So in RISC there are reduced instruction, means less number of instructions. CISC, complex but more number of instructions are there. So the instructions are pipeline and more increase the execution speed. No instruction pipelining feature in case CISC architectures. So and then the RISC have performed more number of registers availability, and even here it is a less number of limited general purpose are there. If you take an example for RISC, ARM has around 16 different registers, R0 to R15, and in case CISC example is 8086, we have AX, BX, CX and DX. So there are 4 general purpose registers available for our ALU, for our function implementation corporation. And all in RISC, all the operations are carried on the registers only. But in case 8086, we can do, the instructions are designed like that. So all the operations can be done either completely using the only with registers or register and memory combination. Single and fixed length instructions. Here the CISC has a variable length instructions, whereas RISC a less silicon usage and pin count are in usage is more compared to the RISC. So most of the time RISC processors are Harvard architectures, and CISC processors can be Harvard or von Neumann architectures. So one more thing we have to know about the processor and the controls, the kind of the way it stores the data on the memory. NDNS, the order in which the sequence of bytes are stored in computer memory. So there are two types, little endian or big endian. So little endian means the lower order byte of the data is stored on the lower address memory location. So that is explained very well with this example. So here the memory and its addresses. So the base address here it is taken as 1000, and the next higher address locations addresses are location address are 1001, 1002 and 1003, and the data's lower byte naught is stored at the lower address 1000, and next higher bytes are stored at the next higher addresses. There is one example here. So 90AB12CD is the data which is stored on the memory. So on 1000 they stored the CD lower address lower data, and 90 is some most higher byte of a data stored on 1003 address. After the big endian style, the higher byte of the data is stored at the lower address. That is also it's better we try to understand with example. So here the base address 1000 and its next higher addresses locations are 1003. The base address location stored byte 3 and at a higher address 1003 the byte 0 is stored. So here you can make out the difference. So next is the differences between we have to make out the differences between Harvard and von Neumann architectures. There are the two Princeton universities of the US, Harvard and Princeton, come with the architectures. So the Harvard architecture suggests the separate address and data bus for data memory and programmable. But in case of von Neumann, also called referred as a Princeton architecture sometime, has suggested only single bus is shared among IO, CPU and memory. So we will make out the differences. So Harvard architecture separate bus for instruction as well data fetch, as you see in the block diagram. A single bus is shared. In case von Neumann, in Harvard easier to pipeline, but in low performance compared to the Harvard. comparatively very high cost. Harvard has a very high costly, Van Neumann cheaper, because as we have to separately connecting address line, data line and control lines for data memory as well program memory, the bus connection cost will increase compared to Van Neumann. No memory alignment problem in case as the both are separately connected by separate address line, data line and control lines. But in case Van Neumann, maybe some time we need a modifying code. Load store operation and instruction pipeline. So, load store operation, for example, we will take a RISC processor is explained here to explain a load store operation and instruction pipelining. And ARM Cortex M3 with a RISC controller, and as you know the Cortex M3 controller always do the addition or ALU operations, arithmetic or logical operations, uses the stored operand in the register only, as in the other counterpart the processor 8086 what we studied, where we use the even memory mentioned in case that indirect addressing mode in instruction add a sub. So, here the 3 register R1, R2 and R3. So, the data is fetched and stored on the R1 and R2, and after ALU operation the data again stored back to R3 and then later stored to memory. So, we cannot deal ALU arithmetic and logical operation directly with memory. So, instruction pipelining. So, this shows the instruction pipelining for single stage. Single stage for every machine cycle we fetch that always all the processor will fetch, decode and do the execution operation. So, for every machine cycle one single instruction is fetched from ROM, then it is decoded for which operation it has to do, and accordingly the data is fetched from the RAM and then it is executed. That is shown here. For every machine cycle one instruction is executed. But if you do the instruction pipelining, here it is shown the 5-stage instruction pipelining. So, the stages are fetch, decode, read operands, execute and write back. So, here when the instruction 1 is written back, executing, fetched, first interval of time, that time T2, the second instruction is fetched, at that time T1 is decoded. At time T3 the third instruction is fetched, second instruction decoded, and for to execute the first instruction the operands are read from the ROM. And at time T4 the fourth instruction is fetched, third instruction is decoded, second instruction fetches the operands and first is executed. After executing, when the results are generated, that result is stored back in the next T5 side time, T time. So, that is I1 store back, at that time I2 executes, I3 instruction fetching the for I3 instruction execution data is fetched, and I4 instruction decode, and I5 instruction fetch from there. So next is PLD, programmable logic devices. The programmable logic devices are of two types. So fixed and programmable. Fixed circuit is permanently fabricated, and then programmable, you are allowed to configure according to. So while doing the Verilog HDL lab, you have used FPGA and CPLD. They are the best example for programmable logic devices. So here they are used for prototyping. For example, if you suppose you want to fabricate the adder IC, then you have written a program in Verilog, and then you have dumped on a FPGA, and then prototype is ready, and then you test it. The tested code or design, if it is work according to your requirement or a function what is given to you, assigned to you to design IC, then if it is fine, then it is sent to fabrication to the fab. So the programmable logic devices offer customer a wide range of logic capacity. That is what I am saying. So you can reprogram or reconfigure every time the FPGA and CPLD for making the prototype for different circuits. So designers can use inexpensive software tool to quickly develop, for example, Xilinx Project Navigator what we have used, and simulate, and then send the logic design, right, to fab for fabrication. So here FPGA, and FPGA is a complex programmable logic device. The two major types of FPGA, programmable logic devices, FPGA and CPLD. Second one is CPLD, is complex programmable logic devices. FPGA offers high amount of logic density and the most features and high performance, okay, and built-in hardware processors. CPLD offers small amount of logics compared to FPGA and predictable timing characters, and therefore the ideal for the critical control applications, the CPLD. Commercially off the shelf component, and is also is a product is one which is used as is means as it is. So for example, I will while doing the final year project, you will bring some components which are ready made available in the market, built in, what you can call it. They are called codes. The best example for what I can give for codes is the mouse, wireless mouse. It's a dongle, and a wireless mouse and a dongle are communicating, right, and the wire, and when you bring the wireless mouse, buy a wireless mouse, and directly if you insert that dongle into the USB slot, so it automatically start working. It will take some time, it will load the software what is required, and then immediately start working. So such products are called as an off the shelf. The typical example for hardware units are remote control toy car, control units which are RF circuitry parts what are used in that building the toy are ready made available. Simply you have to bring those component and you have to use in the development of your toy, that we call, even that is also embedded system. And the code internally has maybe a general purpose processor or application specific instruction processor or the ASIC or even sometime PLD. So, the major advantage of the codes is readily available. Simply you have to bring and make use, and very cheap. You need not to build those for your project or building of making an embedded system. And the major drawback of this code is, so if the vendor designed for a specific operator or a specific component, if you are building the 1000 units, if in between he stops manufacturing, then it become a problem for you. That is the only thing what major drawback of this codes. Okay. Thank you. In the next video, watch for part 2 of this, where I will explain the chapter 2 typical embedded system of Introduction to Embedded System by Shibu KV book. That next video I will cover the